Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. Today we are going to take up a very impactful reaction which is the hydrogenation of alkenes, and which represents one of the finest demonstrations of the utility of organometallic complexes in homogeneous catalysis. Now, if one looks at hydrogenation of olefins, hydrogenation of olefin is sort of complementary to oxidation of olefins. Is complementary to oxidation of olefins, and what we had seen is that oxidation of olefins is in fact very well extensively studied, particularly from the industrial perspective. Oxidation of olefins, we have discussed lot of large scale utility. For example, Wacker reactions where ethylene was oxidized to acetaldehyde, or these epoxidation reactions where olefins were oxidized to epoxides, which are useful intermediate to ethylene glycols. So, oxidation of olefins is in fact a very important reaction to perform from an industry perspective in large scale processes, and we have seen several industrial processes like Wacker oxidation, which is known for more than 100 years or so, or this Halcon-Arco oxidant process of epoxidation, where propene is converted to propylene oxide, that too in huge amounts by these chemistry which represents oxidations of olefin. So, as we had seen that oxidations of ethylene is quite important, and there are several industrial processes which are important with respect to this olefin oxidation chemistry is concerned. On the contrary, this when we look at the complementary reactions, which is reductions of olefin, which is represented by this reaction, which is hydrogenation of olefin. Hydrogenation of olefin is nothing but reduction of olefin. That also is equally important from industrial point of view, because lot of chemistry is designed against the olefin hydrogenation reaction. Also complementary towards this olefin hydrogenation reaction is this olefin oxidation reactions, with which we are comparing this reaction in back and forth. So, I would like to note that olefin oxidation reaction is thus an attempt to convert olefin to other oxygenated useful chemicals, chemical intermediates, which can which are of relevant importance to various synthesis of various organic targets. So, with that now we are going to focus today's lecture on hydrogenations of alkenes, and we know as has been mentioned that hydrogenation of alkene is just a complementary reaction to that of oxidation of olefins. Now, in the hydrogenation of alkenes, the primary step of interest of course is the dihydrogen activation, and how does dihydrogen gets activated by transition metal complexes in homogeneous solution. And one needs to look at ways and means in which the dihydrogen can be activated in solution, and this actually can be done in 3 different ways. So, we are going to look at it in bit more details. Dihydrogen activation in homogeneous solution can be achieved by three different pathways. And we are going to discuss this in bit more details. These three different pathway involves homolytic cleavage of hydrogen, heterolytic cleavage of hydrogen, and oxidative oxidation using hydrogen. So, three different pathways are homolytic cleavage, and that is represented by this equation 2 CO CN 5 3 minus plus H2 giving 2 CO CN 5 H 3 minus. So, this is a homolytic cleavage. It means that dihydrogen is splitting into 2 hydrogen atoms. The next comes heterolytic cleavage. Heterolytic cleavage of hydrogen means that dihydrogen is cleaved as H plus and H minus. So, it is cleaved as a proton and a hydride, and an example of heterolytic cleavage is platinum SnCl3 whole 5 3 minus plus H2 giving H Pt SnCl 3 whole 4 3 minus plus H plus SnCl3, and next come oxidative addition, and where oxidative addition is just oxidative addition of hydrogen to a metal center. This is like any other oxidative addition reaction. Oxidation. And this is given by the reaction PPH3 whole thrice rhodium chloride plus H2 giving PH3P rhodium H2Cl. So, this is three different this is a way of cleaving hydrogens. So, what we saw that there are actually three processes that are prevalent by which hydrogen can be activated. Now, one of the first hydrogenation catalyst is this Wilkinson catalyst. The good thing about Wilkinson's catalyst is that it can carry out hydrogenation of olefins under very mild condition. Catalyst, which is of the formula PH3P whole 3 rhodium chloride, and it involves the way it functions, it involves oxidative oxidation method of dihydrogen activation, involves oxidative oxidation method of dihydrogen activation, and hydrogenations of alkene and alkynes occurs at 25 degrees centigrade under standard pressures. Hydrogenation of alkenes and alkynes occur at 25 degrees centigrade and standard pressure. So, what does that mean is that this is quite a highly active catalyst which can not only activate dihydrogen, but also add across these unsaturated substrates like alkene and olefin at a very mild condition of 25 degrees centigrade, that is the room temperature and standard pressure. And the catalyst also carries out terminal double bond faster than internal bonds. Terminal olefins hydrogenated faster than internal ones. This also is functional group tolerant. Groups like NO2 and CHO. So, functional group tolerant, and this cis addition, the dihydrogen addition happens in a cis fashion. So, cis fashion. So, these are few attributes of this homogeneous catalyst, which is this Wilkinson's catalyst. Wilkinson's catalyst is a rhodium 1 triphenyl phosphine rhodium chloride, tris triphenyl phosphine rhodium chloride. It involves oxygen activation by oxidative addition method. This oxidative addition occurs in a cis fashion. The hydrogenation conditions are really mild at 25 degrees centigrade and standard pressure. So, that gives a very good efficiency for this catalyst. Hydrogenations of terminal double bond occur faster than hydrogenation of internal olefins. Catalyst is functional group tolerant, and dihydrogen addition occurs in a cis fashion. So, these are key attributes of this Wilkinson's catalyst, which is nothing but alkene and olefin hydrogenation catalyst. And then we are going to look at the mechanistic pathway following which this Wilkinson's catalyst function. So, the catalyst starts from R3 P3 or HCl. P equals triphenyl phosphine that loses a phosphine to give rhodium P chloride. So, this adds dihydrogen. So, this is the oxidative addition to give rhodium chloride P phosphine H. So, this step is the oxidative addition step. And subsequent to that, the oxidative addition is the olefin coordination R CH2 giving R rhodium P Cl H H. So, this is nothing but the olefin activation step, or can be said as coordination step. Subsequent to this coordination, the migration of the olefin to this rhodium hydride bond leading to the formation of rhodium alkyl reagents are formed. So, this olefin migrates into one of the two rhodium hydride bond to give this rhodium alkyl moiety. So, this step is the migratory insertion, or called the insertion step. Subsequent to the formation of rhodium alkyl, the next step involves this rearrangement of this cis and trans geometrical isomers, where this rhodium hydride phosphine compound rearranges to P CH2 CH2R. So, this is can be thought of as like a geometrical rearrangement, Cis-Trans rearrangement, and this step is called the Cis-Trans rearrangement step. Cis rearrangement step to finally the reductive elimination step, where this alkyl and hydrogen reductively eliminates to give the hydrogenated alkane R CH2 CH3, along with the formation of the initiating precursor, which is rhodium P2Cl. So, this is the reductive elimination step. Now, of these step, this third step is the rate determining step, which is the insertion of the olefin into the rhodium hydride bond. So, this is the rate determining step, which has been proposed based on computational study, that this migration of coordinated olefin to a rhodium hydride bond is most likely be the rate determining step of this catalytic cycle. So, what one sees that this Wilkinsons catalyst is a good hydrogenation catalyst, which can function at room temperature and standard pressure, and also it does hydrogenation of terminal olefin faster than the internal olefin, and the mechanism consists of 4 elementary steps. The first one being oxidative addition, followed by coordination, then insertion, then 5 steps. The catalytic cycle consists of 5 elementary steps. First one is oxidative addition, coordination, insertion, Cis-Trans rearrangement, and reductive elimination. Of the different steps, the third step, which involves migratory insertion of the coordinated olefin on a rhodium hydride bond, is supposedly the rate determining step of this reaction. Now, one important attribute of this Wilkinsons catalyst, that it can carry out hydrogenation of terminal as well as internal olefins. However, the internal olefins is hydrogenated at a slower rate. PH3P whole 3 rhodium chloride, which is Wilkinsons catalyst, can hydrogenate both terminal and internal olefins, though the internal olefin is hydrogenated at a slower rate. However, this another catalyst which has 2 ppH3 rhodium carbonyl chloride catalyzes highly selective hydrogenation of terminal olefin. So, this is an interesting observation, that if one modifies the catalyst from Wilkinson's catalyst that has 3 triphenyl phosphine and 1 chloride attached to rhodium, which can hydrogenate both internal as well as terminal olefinic bonds, to bis triphenyl phosphine rhodium carbonyl chloride, which catalyzes highly selective hydrogenations of only a terminal olefin. Though Wilkinson catalyst is extremely good catalyst with high efficiency, one of the drawbacks of Wilkinson's catalyst is its selectivity, and that can be achieved if one modifies the catalyst a bit to 2 triphenyl phosphine rhodium carbonyl chloride, which can selectively do hydrogenation of terminal alkenes. And this is explained by this catalytic cycle: rhodium P H CO P P P equals PPH3 loses 1 triphenyl phosphine to give this rhodium square planar complex PPCO hydrogen. So, the first is that the terminal olefin coordinates to this square planar complex to give a 5-membered P rhodium CH2 CHR H CO. So, this is a coordination step followed by this insertion of the coordinated olefin to the rhodium hydride bond, giving rhodium P CH2 CH2R and CO. So, this step is the insertion step, followed by hydrogen addition, which is an oxidative addition. This addition occurs in a cis fashion, as has been mentioned for the Wilkinsons catalyst, and proceeds in the same way. So, we have this oxidatively added cis dihydride moiety attached to rhodium CH2, CH2R, CO, and then 2-phosphine in cis orientation, and that reductively eliminates to give the desired product CH3 CH2R, and giving back the initial starting active species, which is bisphosphine rhodium hydrochloride. So, what we see that the selective hydrogenation of terminal alkyne can be carried out with this catalyst of rhodium bisphosphine carbon monoxide hydride, and that it can hydrogenate terminal alkenes in 4 elementary steps. The first one involves coordination of the olefin, the second one involves insertion of the coordinated olefin to the rhodium hydride bond, then subsequently oxidative addition of a dihydrogen molecule, followed by reductive elimination to give the desired reduced product. So, with this I would like to conclude today's discussion on hydrogenations of alkenes. As mentioned in the beginning of the class, hydrogenation of alkenes is an yet another big discovery which is practiced in the industrial scale, and hydrogenation of alkene is nothing but the complementary of alkene oxidation reactions, which two are also equally important from industry's point of view. We have looked at the types of hydrogenation reactions, hydrogen activation pathways, and what we had seen that the hydrogen activation pathways proceeds in 3 ways. First is the homolytic cleavage, second is heterolytic cleavage of dihydrogen, and lastly it occurs by oxidative addition. And then we have looked into one important example of hydrogenation of olefin reaction, particularly using Wilkinsons catalyst, which can carry out hydrogenations of terminal as well as internal olefins and alkynes at mild conditions and normal pressure, and then though the internal olefins are hydrogenated at a lower speed, and then we looked into this catalyst which is bis triphenylphosphine rhodium carbonyl hydride, which can carry out this hydrogenation of selectively terminal olefins in the similar catalytic pathway. So, with this I would like to conclude today's discussion on hydrogenation of alkenes. We are going to talk more about hydrogenation of alkenes for chiral, achiral as well as chiral system when we meet next. I sincerely thank you once again for patiently listening to me in this lecture, and I look forward to being with you in the next lecture when we complete the remaining part of hydrogenations of olefin reactions. Thank you.